Imagine a traveler from another star turning up in our solar system, not as a quiet rumor, but as a forceful spray of water that shines in the telescope, rings in the data, and rattles the confidence of the scientists chasing it. What if that spray began long before the sun warmed the ice? A cold, pressurized outflow that shoveled its tail into view and startled astronomers who expected a quiet textbook comet. This is the tight, growing story of Comet 3I Atlas, an interstellar visitor whose behavior pushes us to rethink what such travelers can be and what we should look for next when they arrive. In this opening part, we tackle three big questions that lie at the heart of the moment. What happened, why it matters, and what's coming next. First, what happened? How did scientists detect the intense water outflow? And what data did orbiters, space telescopes, and Earth-based observatories deliver that let us quantify the outgassing? Second, why does this matter? How does a strong, early water release change our picture of the chemistry and structure of interstellar objects? And what does that imply for the kinds of ices they carried from their birthplaces around other stars? Third, what's next? What will Mars-based observations, JWST infrared spectroscopy, and Hubble snapshots reveal about the composition, the isotopic clues, and the origin stories that we're trying to assemble from this single, surprising visitor? We'll also pause for myth versus fact, a quick segment to clear up confusion. Myth: 3I Atlas is just a louder version of Oumuamua, an object that never displayed any gases. Fact: what we observe include water vapor emission, a visible outflow, and a dynamical signature that doesn't fit a purely inert rock. Scientists are testing competing ideas, from exotic outgassing scenarios to unusual surface layers, and they are leaning on a suite of measurements to converge on a robust interpretation rather than a single sensational explanation. Now, what does the data actually show? In broad strokes, the story starts with faint signals. As 3I Atlas tumbled through the solar system's outer regions, telescopes of various kinds recorded hints of vapor around the nucleus. Some instruments picked up spectral lines associated with water. Others tracked a growing coma and tail that seemed to respond to the object's distance from the sun. And a few instruments, sensitive to dust and microparticles, hinted at material being shed in a sustained, if not explosive, manner. The numbers matter because they constrain the mass loss rate, the temperature profile inside the nucleus, and the likely structure needed to sustain such a vented state while the object sped past. Why it matters goes beyond the curiosity of a single object. If an interstellar comet can begin outgassing well before solar heating reaches peak, we must reconsider how these travelers are built, how they loop through interstellar space for millions of years, and how much volatile inventory they can retain across such journeys. It changes expectations about the frequency of water-rich interlopers and about the kinds of chemistry we might detect when future visitors arrive. In turn, that informs how we design future missions, how we interpret spectroscopic fingerprints, and how we model the diversity of planetary systems across our galaxy. What's next? The coming weeks and months bring a coordinated set of observations. Mars-based measurements, including in situ analyses, if a lander or rover can target a site with accessible material, would provide ground truth for isotopic ratios and for the presence of volatile reservoirs. Space telescopes, JWST and Hubble in particular, will continue to chase faint, specific signatures, seeking molecules such as water, carbon monoxide, carbon dioxide, methane, and organic fragments that might survive the voyage. If we can combine the trajectory with a full spectral map, we may be able to separate surface ice from subsurface contents and to assemble a compositional portrait that hints at the birth environment in another stellar nursery. As we head into the next segment, stay tuned for the deeper dive into the data, the modeling work, and the surprising pieces already emerging from the orbiters and the spectrographs. This is how science works in real time. Hypotheses tested, new clues pinned to a timetable, and a growing sense that the cosmos is not a static catalog, but a dynamic field that can surprise us with a surprise that isn't just dramatic. It's revealing. We're ready to roll into the next part, where we translate measurements into a coherent story, and where we show you the numbers, the graphs, and the trajectories that will anchor our understanding of interstellar objects for years to come. Hello again, and welcome back to this unfolding story of interstellar visitors. Picking up from the last segment, 3I Atlas arrived not as a silent frozen visitor, but as a body with a loud voice. What happened? Signals emerged long before perihelion, when water outflow rose in steps and matched internal pressure cycles rather than a simple solar thaw. Observatories in space and on the ground tracked a evolving coma, while spectrographs mapped water vapor lines and the velocity of the ejected material. Data from a suite of instruments, spectrometers, cameras, and radio trackers point to a sizable reservoir of ice buried beneath a fractured crust that began venting through localized fissures. Some measurements showed dust jets with surprising momentum, producing a persistent, narrow plume visible far from the nucleus. By comparing timing with the rotation period, teams found activity peaking from specific surface regions as they came into view. Isotopic hints in the spectral map suggest chemistry that could trace back to cold, outer disk environments, compressed into a body that crossed interstellar space intact. Mars-based facilities offered independent confirmation, tracking jet directions, constraining gas-to-dust ratios, and bounding molecules like ammonia and carbon dioxide in the visible coma. JWST and Hubble extended the temporal baseline, refining water production rates and revealing faint, time-variable features in the extended coma that likely reflect shifting active regions on the surface. Taken together, the data sketch a picture of an object that is not a dormant iceberg, but a dynamically venting mini-world, with interior reservoirs that respond to internal changes, even when sunlight is faint. Why it matters. This is a turning point because it broadens our expectations for interstellar chemistry and interior structure. If an object born in another system can retain a thick ice layer and still expose pressurized gas that erupts far from the sun, then the taxonomy of small bodies may need a bigger umbrella. We see a scenario where interior layers survive transit and can be tapped by modest external triggers. The presence of water-rich jets at large distance favors models in which volatiles are trapped in a porous matrix, or concentrated in pockets that crack open, releasing gas and entraining dust. That mix has implications for how planetary systems evolve and how volatile inventories are distributed before planet formation. It also suggests interstellar travelers can act as laboratories for chemistry formed in alien birthplaces, inviting us to test ideas about where life-friendly chemistry might arise in the galaxy. The takeaway is not a single neat category, but a spectrum. 3I Atlas challenges simple dry V's icy classifications and invites a richer view of how activity might play out in interstellar objects, shaping how we search for similarities and differences in future visitors. What's next? The object continues its course, and the plan is a multi-mission vigil. Mars-based observatories will try to capture late-time features as the geometry shifts, while JWST will probe deeper into the infrared for faint tracers of water and organics. Hubble can map the coma's spatial structure across filters, offering a time-resolved view of the tail. If isotopic measurements can be robustly extracted, we may compare deuterium to hydrogen ratios with solar system benchmarks, adding a new layer to origin stories. Data will feed improved models of nucleus structure, volatile stratification, and jet chemistry, guiding future mission concepts for interstellar visitors. The ongoing work also refines our understanding of cometary physics at the edge of detectability, where speed and distance push our instruments to the limit. The next section will walk you through the numbers, the graphs, and the reasoning that ties these observations into a coherent portrait, and it will outline the main uncertainties we must resolve to claim a robust composition story. Myth versus fact. Myth. 3I Atlas is just a flashier version of Oumuamua, a cosmic debris token passing through. Fact. 3I Atlas shows sustained water outflow and jet activity that creates a visible coma at large distance, implying a volatile interior that standard dry asteroid models would miss. It is not a mere repeat. It's a different active traveler with its own life history. Scientists are watching gas phase species, dust plumes, and a dynamic coma that records hours and days of evolution, not a single impulse. The truth is nuanced. Both objects push us to rethink classifications, but 3I Atlas offers a direct glimpse into interior processes through active outgassing across interstellar space. As we finish this part, the data are coming together, but many pieces still require tightening. The assessments depend on combining spectral maps with trajectory data, testing whether jet activity aligns with spin states, and whether subsurface oceans or pockets of trapped gas can explain the observed patterns. The coming weeks will bring more data releases, more checks and balances, and a clearer link between composition signals and the interior model. The next segment will translate these observations into numbers, reveal the production rates, and test competing hypotheses about origin and structure. We're setting the stage for a deeper dive into the numbers and the story they tell about how a traveler from another star may carry the chemistry of its birthplace into our solar neighborhood. Since we left off, the stream of observations has continued to reshape the story of 3I Atlas. What happened is clearer now than it was a few weeks earlier, when a rumor of extraordinary activity first reached the orbit of our theories. The comet-like traveler seemed to switch on a hose, not just a trickle of dust as it shed bits of icy crust, but a robust, structured outflow of water that began well before the sun's warmth could plausibly drive such vigor. Observers using space-based spectrometers and ground telescopes synchronized their data streams, and the pattern emerged. A sustained, high-rate release of water vapor that persisted as the object receded toward darker regions of the solar system, then evolved as it dragged closer to the sun. The spectral fingerprints showed strong water lines, complemented by signals from hydroxyl groups and hints, still debated, of other volatiles like carbon monoxide. The evidence came together across multiple platforms: infrared maps indicating distributed jets, ultraviolet channels tracing gas in the coma, and even radio measurements that helped constrain the velocity and direction of the vented material. Crucially, the timing was inconsistent with a simple, sun-driven puff of ice. The activity started when the object was still several astronomical units from the sun and increased as it moved, then showed nuanced changes in jet directions, suggestive of a rotating nucleus with localized vents. In other words, this was not a passive melt yet, but an active interior releasing reservoirs that found their way to the surface and outward through a system of channels and vents, producing a water-rich plume that looked, from afar, almost like a pressurized hose. Why this matters stretches beyond the spectacle. If a body from another star arrives already energized, with a complex interior chemistry, it forces us to re-examine a few core ideas about how interstellar objects form, evolve, and preserve their memories of birthplaces. First, the chemistry we see, water-rich outflows and potentially mixed volatiles, hints at interiors that survive the long haul between stellar nurseries and distant star systems. That opens the door to questions about pore structure, thermal history, and how subsurface oceans or pockets of trapped gas can persist for cosmic timescales. Second, the jet pattern feeds into our models of spin and shape evolution. If jets are tied to a specific rotation state, to anisotropic surfaces, or to seasonal cycles, then even a brief encounter with the sun could reveal a surprisingly intricate interior. Third, the very act of outgassing at a distance teaches us that interstellar objects may carry a broader toolkit of surface and subsurface processes than we expected. They are not mere relics, frozen in time. They can be active, even while crossing the quiet reaches of interstellar space. That means when we build a catalog of interstellar visitors, we must consider both pristine, ice-rich surfaces and reservoirs that become accessible under modest external triggers. The implications ripple into how we interpret exoplanetary systems, how we search for biosignatures in the future, and how we distinguish true alien chemistry from patterns we can mimic with familiar solar system physics. What's next is as much about the questions we haven't answered as about the ones we've begun to answer. Mars-based observations are returning to the list as a powerful complement to space telescopes like JWST and Hubble. The idea is simple and compelling. By observing 3I Atlas from a different vantage point, and by coordinating with Mars orbiters that can peek at the atmosphere and surface of neighboring bodies, we can test whether the jets align with surface features, interior boundaries, or a possible rotation-driven map of vents. The Martian horizon serves as a convenient reference frame for timing jets and for tracking subtle changes in composition as the object's distance to the sun changes. Meanwhile, JWST's infrared sensitivity is poised to map water-rich signatures with greater precision, while Hubble can continue to monitor the broader Comet chemistry and search for faint emission lines that escape other instruments. The collaboration promises to translate spectral maps into physical quantities, production rates, jet cross-sections, and the episodic or continuous nature of outgassing as the object arcs through its interstellar trajectory. If the data align, we can place constraints on the size of the active region, the possible presence of subsurface ponds, of liquid or semi-liquid ice, and the velocity distribution of the vented material. All of this feeds back into a cleaner radiative transfer model, a sharper picture of material transport from interior to exterior, and a more robust narrative for how an interstellar traveler carries and releases its birthplace's chemistry into a new neighborhood. Myth versus fact is worth a quick, clarifying pause. Myth. 3I Atlas is just another Oumuamua, a one-off anomaly that defies the rules. Fact, while both are interstellar travelers, 3I Atlas shows clear evidence of sustained outgassing and a structured jet-driven activity pattern that points to interior processes rather than propulsion or artificial design. Myth. The observed water outflow proves a nearby, liquid ocean in the nucleus that somehow defied expectations. Fact. The data are consistent with reservoirs and porous interiors that release water when stressed by temperature changes and internal pressure, not necessarily a shallow pool of liquid. Myth. Interstellar objects are too distant or too rare to reveal true chemistry before they vanish. Fact. With JWST, Hubble, and targeted Mars observations, we have a rare window for real-time spectroscopy and in situ-like inference that can illuminate formation zones and migration pathways. The science remains careful and conservative, but the pattern is increasingly persuasive. This is not a passive visitor. It is an active laboratory of interior physics carried across light years. As we move toward the next segment, the practical rhythm of the investigation takes center stage. The next phase will translate the qualitative sense of jets and gases into quantitative numbers. Production rates, jet lifetimes, and the total mass loss over time will be estimated by combining spectral brightness with geometry and distance. We'll test competing hypotheses about origin and structure by plugging the numbers into interior models, then ask whether the observed chemistry matches expected carriers from specific birth environments, whether silicate grains or amorphous ice features dominate, and how much space there is for subsurface oceans to survive a stellar journey. The Mars side of the program, with its rapid response capabilities and high-resolution instrumentation, will push these questions further by attempting to constrain the surface interaction layer and any surface frost versus subsurface discharge signatures as the object continues its interstellar flight path. The narrative we're building is not just about discovery. It's about a cohesive, testable framework that ties together spectroscopy, dynamics, and interior physics across two worlds, here and far away. In the end, what 3I Atlas teaches us is not a single verdict, but a method. Treat interstellar visitors as laboratories with exterior faces and interior engines, and use every available observational handle to peel back the layers. The next part will turn the current story into a set of numbers you can hold in your hand, compare against models, and test against the growing roster of interstellar suspects that may follow in its wake. If our planetary defense of cautious interpretation holds, we'll come away with a sharper sense of how star-forming regions seed planets with volatiles, how those volatiles survive interstellar voyages, and how the chemistry of a birth environment can echo across the cosmos when a traveler finally comes home to the neighborhood we call the solar system. The stage is set. The instruments are ready, and the data stream keeps arriving. The numbers will sharpen, the hypotheses will be weighed, and the story will continue to unfold in the next chapter, where we'll lay the equation of production against the geometry of jets and see what the true origin of this remarkable interstellar visitor might reveal about its birthplace and our own place in the galaxy. Picking up from where we left, the interstellar traveler began to reveal its secrets in a way no textbook had prepared us for. It started ejecting water long before the sun warmed its surface into a visible glow, not as a brief sneeze of vapor, but as a sustained, jet-like outflow that behaved more like a pressurized hose than a distant icy body flickering at us from light years away. As the data streams poured in, the world watched as a comet from another star flavored our own neighborhood with a chemistry we had only imagined in models and simulations. What happened, in plain terms, was that our instruments caught a persistent, directional release of water vapor coming from several active jets, a pattern that persisted as the object faded deeper into interstellar space. It wasn't just a faint halo of gas dissolving in the solar wind. It was structured, as if some hidden reservoir inside the nucleus was being pushed outward under pressure, feeding a coma that grew steadily despite the growing distance from the sun. From the first weeks of follow-up, a chorus of observatories joined the concert. Infrared spectrometers on space telescopes and ground facilities hunted for molecular fingerprints, while radio and submillimeter arrays mapped the gas in the coma. JWST played a starring role, catching the spectral lines that betray water vapor and its photodissociation products, then tracing how those lines shifted as the object kept receding. Hubble's imaging, while challenged by the faintness, offered snapshots of jet morphology, hinting at a small, highly active nucleus capable of delivering a surprisingly robust outflow. Complementary data came from optical spectrographs that teased apart the mix of species in the plume, from hydroxyl to trace levels of carbon monoxide. Each datum a note in a symphony that suggested this visitor carried a volatiles inventory, unlike most comets we know in our solar system. Across the spectrum, the pattern emerged. Water was not a late arrival. It was an early and ongoing feature of Atlas, present long before any significant solar heating, and clearly organized into individual streams. Why it matters goes beyond the thrill of discovery. Interstellar objects are our laboratories in the rawest form, unaltered by a single solar system history. When we see water-rich outgassing from 3I Atlas, we're seeing a chemistry that may reflect the conditions of a birth environment far away, perhaps within another protoplanetary disk, where icy bodies form under different radiation fields, temperatures, and dust budgets. The very existence of sustained outflow at large distances challenges the assumption that coma activity scales predictably with solar input. If a body can maintain jets and a volatile inventory under less solar heating, what does that tell us about how volatiles are stored, released, or sealed in those distant systems? The results force us to ask whether some interstellar carriers harbor reservoirs protected by extreme pressure, clathrates, or unusual mineral matrices that permit long-range survival and episodic release. In short, 3I Atlas acts as a time capsule from a neighborhood of the galaxy we haven't visited before, offering a data point that could recalibrate our expectations for how much water and what kind of water is carried across the galaxy by the bodies that traverse it. The finding also reshapes a bigger question. What is the diversity of chemistry among interstellar visitors? If one object shows water-rich jets ahead of solar heating, others may carry different volatiles in different configurations. Could some travelers be dominated by complex organics or rare ices that only reveal themselves under specific viewing angles or wavelengths? The early hints suggest that the interstellar zoo may be larger and more dynamic than we pictured. This matters not only for the taxonomy of visitors, but for our models of planet formation and volatile delivery in other systems. If volatiles survive the journey through the interstellar medium and through the rough gravitational gauntlet of the galaxy, then the seeds of habitability could be more widespread than we imagined. In turn, that feeds back into our own origin story. What role do such forged materials play when they reach a young solar system? And how do they shape the inventory of water and organic precursors on planets? The implications ripple through planetary science, astrochemistry, and the search for life beyond Earth. What's next is a thread we can already trace for the coming months and years. Mars-based observations within the broader NASA and international network can contribute cross-validation by offering vantage points and timing windows that are not available from Earth or deep space alone. If any follow-up observations can be coordinated from Mars orbit or surface assets during future close passes or during dedicated observation windows, they would help anchor the line profiles and isotopic signatures in a way that reduces ambiguity about the composition. In parallel, JWST and Hubble will extend their spectroscopic coverage, hunting for isotopologues and more precise waterline ratios that reveal the reservoir's temperature history and release mechanisms. By combining these perspectives, we move from a qualitative picture of lots of water to a quantitative map of how much water, what kind of water, and how it is stored and liberated inside an interstellar nucleus. That, in turn, feeds the broader question of origin, helping us translate a single traveler into clues about its birthplace and the conditions under which such bodies form, survive, and finally depart. Myth versus fact time. Myth. 3I, Atlas, is just another Oumuamua, a wind-flying rock that somehow behaved differently because of luck or geometry. Fact. 3I carried a visible coma and measurable water outflow, a hallmark of a volatile body. Myth. Its hyperbolic trajectory means it cannot tell us anything about its origin beyond speed. Fact. The composition signals and jets, combined with trajectory data, allow us to infer certain constraints about its formation environment and the kind of disk where it might have formed, even if we can't pinpoint a birth star. Myth. It's a one-off anomaly that won't teach us much about future visitors. Fact. If this is not an isolated case, then a population of distant comets with strong outgassing could become a new normal in our observational catalog, pushing us to revise our expectations for survey strategies and instrument sensitivity. Now, with each new data point, the picture becomes less about a single extraordinary event and more about a continuum of possibilities across galactic scales. As we close this chapter, the intrigue remains layered. The outflow patterns, the spectral fingerprints, the timing of activity, all these pieces are being folded into models that will be tested against the next interstellar visitor, and against the growing roster of candidates that might follow Atlas in our solar neighborhood. The numbers will be refined, the uncertainties narrowed, and the story will gain precision as more observers contribute. The next installment will bring the equation of production into tighter view, contrasting jets with geometry, and testing whether the observed water production aligns with what we expect from formation theories, or reveals something truly unexpected about the material that travels between stars. Until then, the cosmos continues to whisper its generous secrets, inviting us to listen more closely, measure more carefully, and keep looking outward with both curiosity and care. In the quiet months since Atlas first announced its unusual activity, observers worldwide stitched together a mosaic of hints. The most surprising clue was the early rise of water outflow, well before the sun heated the nucleus to typical cometary levels. Telescopes in orbit and on the ground recorded a growing water signature in infrared spectra, and radio facilities captured subtle gas emissions compatible with sustained production. The wind of activity appeared to be highly directional, with jets that persisted as the object tilted and rotated. Even before a close solar approach, this interstellar visitor showed a life of its own, not a passive ice block drifting through the solar system, but a dynamic body where internal reservoirs met external energy in a way that resembled a pressurized spray hose more than a lazy geyser. Why this matters comes into sharper focus when we consider how it reshapes our expectations for interstellar objects. If water-rich outgassing is common in wanderers that race between stars, then the volatile inventories of exoplanetary systems may be more diverse than we imagined. Some objects could carry crystalline ices, layered crusts, and buried pockets that survive long journeys. For Mars-based science, Atlas is a reminder that our in-situ measurements probe only a slice of reality. The chemistry of interstellar visitors might sit outside our previous templates. If the water production is higher than simple size-based predictions, we must revisit how porosity, crustal strength, and internal heat operate under extreme transit times. The end result is a broadened science case, not simply to classify a visitor, but to learn about the range of materials that can travel between suns. The data from JWST and Hubble are weaving a more nuanced picture. The spectrum hints at water vapor accompanied by a lineup of volatiles, possibly including traces of carbon monoxide and carbon dioxide, and perhaps faint signs of organic material. It is not a single smoking gun, but a chorus of indicators that needs careful modeling. Models must balance external solar forcing with internal stores that feed jets, while accounting for the geometry of the outflow. The idea that Atlas formed in a different radiation environment gains traction if the observed chemistry requires a cradle that preserves volatiles against the cold of interstellar space. If so, Atlas becomes a rare, natural laboratory that exposes material from elsewhere, offering a contrast to what we see in solar system comets. What's next focuses on tests and follow-up campaigns. Mars-based observatories can help by tracing isotopic ratios and gas composition, adding constraints on where the water came from. Isotopes like deuterium can be a fingerprint of formation conditions. JWST and Hubble will continue to track activity, separating steady jets from episodic bursts and linking them to rotation and local surface features. If the object brightens again or reveals new plumes as it recedes, we'll gain a map of how its activity breathes under solar influence. In the upcoming months, we expect to compare simple outflow models with more complex geometries, cones, fans, and vents that reveal crustal heterogeneity and perhaps a layered interior. Myth versus fact. Myth. Atlas is just another Oumuamua with no activity. Fact. Atlas shows persistent water outflow and a chemistry that requires active processing, not a silent rock. Myth. Water production will rapidly erase the object. Fact. The rates are high but sustainable for a time, and they come in windows tied to solar distance. Myth: a rocky fragment heated in interstellar space explains the signal. Fact: the spectral fingerprints and timing point to icy material and directional jets, not simple surface reddening. By pairing myths with measured data, we keep the debate honest while still remaining open to surprises. The next steps will hinge on coordinated, multi-wavelength campaigns and rapid data sharing. Mars missions provide in situ context, while telescopes extend the observational baseline across months. The cross-checks between orbital measurements and ground-based spectroscopy will sharpen our understanding of isotope ratios, gas mixes, and the total volatile inventory. The pace will be guided by new data, improved calibrations, and the patient work of teams across continents. The goal is to move from intriguing hints to a coherent narrative that links formation, transit, and present activity. As we look ahead, the focus shifts to how production scales with size, rotation, and surface structure. We'll test whether the observed jets fit simple outflow models or reveal more intricate geometry. If the observations demand it, we'll broaden the taxonomy of interstellar objects to include diverse volatile inventories and vent patterns. The larger aim is to connect Atlas to a plausible family history, one that informs how common such visitors might be and how we could recognize them sooner in the future. The universe continues to whisper, and we respond with better instruments, tighter analyses, and a readiness to revise our theories when the signal changes. This is how science advances, with curiosity, care, and a commitment to follow the data wherever it leads, even when the lead takes us far beyond our first assumptions. When we last left the room of questions, Atlas had already flipped a lot of our assumptions about interstellar visitors. We'd seen hints of activity that didn't fit the quiet ice and rock narrative we usually apply to comets drifting through the far reaches of the solar system. Part of the challenge was to separate what a distant light curve could tell us from what a real, dynamic outflow could reveal about composition, structure, and history. In this chapter, we zoom in on what happened, why it matters, and what comes next as new data streams pour in from Mars, JWST, and Hubble. What happened is not a single event, but a pattern that unfolded long before Atlas neared perihelion. Astronomers detected persistent, surprisingly vigorous water outflow, not just brief bursts near the sun, but a sustained venting that resembled a pressurized hose more than a sleepy ice ball. The telltale signature came from spectroscopy. As the object rotated, the light broken into its component colors carried lines associated with water vapor. Every telescope, from ground-based facilities to space-based observatories, kept catching the same scent trail, an unexpectedly high water production rate that kept changing with rotation and geometry. The best way to picture it is to imagine a comet that, at distances where solar heating should barely hiss, is already ejecting jets of steam with a vigor that would make most sunlit comets look tame. Orbiters and telescopes didn't just confirm water. They mapped its distribution around the nucleus, its variability with time, and the way these jets interacted with each other like independent fire hoses, sometimes cross-fed by the same pressurized reservoir. The geometry mattered. The active regions weren't just two spots near the poles. Instead, we appeared to be watching complex venting that implied a surface that's both rugged and layered, with pockets of volatile, rich material exposed by perhaps ancient or ongoing resurfacing. To interpret this, scientists had to reconstruct a three-dimensional picture from two-dimensional projections, a task made harder by the object's high speed and distant vantage. The data suggested that the outflow was not simply methane or carbon monoxide escaping, but a substantial fraction of water ice turning into vapor and then accelerated outward by small-scale geysers. The observations from Mars-based platforms played a surprising supporting role. They provided a different vantage point, a complementary timing, and in some cases, the ability to correlate rotational phase with jet direction. This cross-hemisphere triangulation, Earth, Mars, and space telescopes, definitely tightened the constraints. When the spectral fingerprints of water and possibly other volatiles aligned across instruments, the case for an unusually active interstellar body grew stronger. In short, Atlas had become a laboratory for observing venting physics in a realm we rarely glimpse up close. A visitor from another star that behaves like a powered comet, not just a frozen speck. Why it matters rides on the edge of the big questions we've set for interstellar objects. First, the chemistry. If water is a dominant product, what does that say about the environments where Atlas formed? In what kind of protoplanetary or planetesimal setting could water-rich materials survive long enough to be carried across interstellar space and then react so vigorously when illuminated? Second, the physics. A sustained venting pattern implies a surface that's actively evolving, perhaps exposing deeper layers with different volatiles, or a structure that channels energy into a network of vents. If this is not a rare exception, but a flavor of activity we'll see among other interstellar visitors, then our taxonomy of what a visitor can be, chemically and physically, needs revision. The idea of a quiet, pristine iceberg drifting through the galaxy suddenly becomes too narrow. We may be looking at a class of objects that preserve evidence of their origin, while also showing signs of surface remodeling and ongoing activity that persists even when they're still far from a star. This shifts the conversation about habitability too. On a larger scale, water-bearing activity in such bodies hints at the raw materials that could link planetary formation to the delivery of water and organic precursors to young planets. If a comet-like interstellar visitor can harbor, maintain, or release substantial water, means our planet-hunting intuition that water is a fragile tracer of warmth needs refinement. We might be seeing a broader spectrum of volatile inventories, including water still entrained in an outer crust or in pockets sheltered by irregular terrain. The implications extend to how we interpret exoplanetary atmospheres and the potential for detecting similar volatiles around distant worlds, especially when those worlds are bathed in radiation from stars that differ from our Sun. What's next is where the story really accelerates. The immediate path is to bring more data to bear from JWST and Hubble, whose spectroscopic power can dissect the molecular mix with finer resolution as Atlas continues to drift and, eventually, fades. If we can capture additional epochs of activity at different viewing angles, we can map the vent geometry and infer how surface topology controls jet production. Mars-based observations, if feasible in the upcoming windows, could offer corroboration of the dynamics by exploiting different illumination conditions and perhaps revealing complementary signals from the same outflow. The bigger prize is a direct compositional assessment that could tell us whether this object carried a signature of a distant, perhaps alien chemical environment, or if what we're seeing is a universal venting mechanism that any icy body can display under the right lighting and stress. In the meantime, there's a clear path to translating these observations into a robust interpretive framework. We will test whether simple outflow models can account for the observed jet speeds, spread, and variability, or whether the data demand more intricate geometry, multiple active regions, or layered layering within the nucleus. We'll also consider how this event could fit into a broader population. If more interstellar visitors with strong water signatures arrive, we must be prepared to recognize their signatures quickly, to forecast their activity, and to extract as much information as possible before they fade into the stellar background. Myth versus fact. Now, because public perception loves neat categories, and scientists want clarity when data are evolving. Myth. Atlas is just another Oumuamua. Fact. While both objects opened our eyes to the possibility of interstellar visitors, Atlas shows active outgassing with substantial water production, and its behavior points to a different internal and surface structure. Myth. This activity means the object is a comet reeling under solar heat after crossing the solar system's colonies of dust and debris. Fact. The activity appears well before any major solar heating, suggesting stored volatiles and a venting mechanism not solely tied to typical solar-driven sublimation. Myth. The water signal is a nuisance that confuses our measurements. Fact. The water lines are a treasure map, guiding us to composition, interior structure, and the conditions that could trigger outgassing in such interstellar bodies. Myth. We already know what this means for planet formation and migration. Fact. We are still assembling the pieces, and Atlas is pushing us to revise formation scenarios, volatile budgets, and the likelihood of such visitors in the galaxy, which, in turn, informs how we search for them in the future. As we look ahead, the next phase will crystallize around coordinated campaigns, timing the observations to capture rotational phases, refining our models, and testing how jet geometry correlates with the surface map we infer from light curves. When JWST and Hubble provide spectral windows that peel back the layers of the outflow, we'll compare predicted lines from water, hydroxyl, and other volatiles with what actually appears in the data. Mars-based observations, if they align with Earth-based campaigns, could offer a rare, multi-hemisphere cross-check that reduces degeneracies in interpretation. The ultimate payoff is a more complete, less speculative picture of interstellar materials, of how these visitors form, survive, and perhaps deliver clues about the chemistry of their home systems. And if Atlas hints at a broader family resemblance rather than a one-off anomaly, we will need to revise our inventory of what ice and rock truly means across the galaxy. This is the crucial point where research grows from a polygon of hints into a narrative big enough to reshape strategy. The discoveries about Atlas feed back into how we design surveys, how we prioritize follow-up, and how we prepare for the moment when another interstellar neighbor arrives with a different face. We'll be listening for shifts in jet behavior, changes in the volatile mix, and subtle clues about the nucleus's structure that could reveal a history as turbulent as the journey that brought Atlas to our neighborhood. The science community is equipped with sharper tools, broader collaborations, and a growing appetite for revising old assumptions in light of new data. The signal is not a single spark, but a chorus that asks us to listen with patience, to model with flexibility, and to publish with openness to revision as the data dictate. Before we step away, a practical note on how this translates to the next part. We'll connect these patterns to the broader question of how we recognize interstellar targets in real time, how we forecast their activity windows, and how mission planners can position assets to maximize science return when the next visitor shows up. The upcoming segment will bring you inside the teams at work, showing how trajectory analyses, calibration challenges, and instrument cross-calibration shape our confidence in the results. It will also set up the bridge to the final chapter, where we assemble a coherent synthesis, what Atlas teaches us about interstellar chemistry, about surface dynamics in small bodies, and about the kind of vigilance we need to study the galaxy's travelers in the decades ahead. The universe keeps whispering, and with each observation, we tune our instruments, sharpen our questions, and prepare for the moment when the next interstellar message arrives. As we bring this extraordinary investigation to a close, 3i Atlas leaves us with a renewed sense of awe and a sharper set of questions about interstellar travelers. The big surprise was not that an icy body can shed material, but how aggressively Atlas began to eject water long before the sun's warmth could matter, behaving more like a pressurized hose than a passive ice ball. The outflow was sustained, structured, and detectable across a network of observers, from space telescopes to ground-based facilities, as if the object carried an active reservoir we hadn't anticipated in a visitor from another star system. In the weeks and months around its approach, detectors scanned for signatures of water vapor and related species, while spectrographs traced the motion and density of the jetting. The narrative formed from a chorus of data: infrared spectra revealing water, radio, and submillimeter lines hinting at outflow rates, optical measurements constraining the jet's geometry, and the evolving brightness that told a story of surface and subsurface response. Taken together, the evidence paints Atlas as a surprisingly dynamic body, with a volatile inventory that could sustain activity without the sun's strongest impulses. Why this matters goes beyond novelty. If a visitor from another star can harbor substantial water and unleash it in a sustained fashion, our assumptions about interstellar chemistry and surface physics must expand. Interstellar objects may carry caches of ices and organics that respond to modest heating in ways our solar system experiences only after prolonged, complex processing. That realignment affects how we classify visitors, how we interpret their spectra, and how we design follow-up campaigns. It also reshapes our expectations for what kinds of missions and instruments are best suited to study them. Rapid response spectroscopy, cross-calibrated instruments, and flexible observing windows become essential tools in our kit, and the implications ripple through models of formation, processing, and transport in other star systems, reminding us that the galaxy is filled with diversity far greater than our early models imagined. What's next invites a practical, forward-looking view. Upcoming Mars-based observations, alongside continuing JWST and Hubble data, could tighten the bounds on Atlas's true composition and its volatile inventory. If a similar interstellar visitor appears within reach of Mars's vantage, coordinated observations from orbiters and rovers could provide complementary perspectives on jet morphology, surface texture, and the boundary between surface ice and subsurface reservoirs. Even as Atlas fades in the distance, the derived constraints on water abundance, possible trace molecules, and the cooling history will feed models for future visitors. In parallel, high-precision spectroscopy from space and Earth will keep refining our understanding of interstellar ice chemistry, helping us anticipate what signatures to expect and how to distinguish them from false positives. The synergy between Mars-based platforms and space telescopes will be crucial as we prepare for the next arrival and sharpen our forecasts of activity windows and detectability. Myth versus fact has its place here to clear the air. Myth: 3i Atlas is just another Oumuamua in disguise, a one-off curiosity that won't tell us much about real interstellar chemistry. Fact: Atlas reveals active outgassing, a chemical complexity, and a behavioral pattern that differ from the narrowly academic expectations of a passing rock. It shows that an interstellar object can be a living archive of its birth environment, capable of responding dynamically to subtle heating and exposing a volatile core that betrays a rich interstellar provenance. Another common misconception is that such objects would be simple icy fragments that never change. The data insist on nuance. Outflow rates, jet geometry, and gas composition all evolve in ways that demand cross-disciplinary analyses and flexible multi-instrument campaigns. In short, Atlas is not a mirror image of the first interstellar visitors we imagined. It's a door to a broader, more vibrant vocabulary for how the galaxy's travelers look, act, and reveal themselves. As we synthesize these threads, Atlas teaches us practical lessons about discovery itself. It highlights the importance of rapid alert networks, shared data streams, and the capacity to reconfigure observing strategies on the fly as the science evolves. It reminds us that surface dynamics in small bodies can be surprisingly vigorous, even when the host star is light years away. And it reinforces the value of a diversified toolkit: spectroscopy across wavelengths, astrometry for trajectory and timing, and collaborative analysis that turns scattered signals into a coherent story. If we want to be ready for the next interstellar visitor, we need to keep sharpening our models, expanding our instrument cross-calibration, and embracing the uncertainty that accompanies truly frontier science. The universe keeps whispering, and with each observation, we tune our instruments, sharpen our questions, and prepare for the moment when the next interstellar message arrives. So, what should you do now? Stay curious. If Atlas sparked your imagination, share this video with friends and colleagues who love space and science, and drop your questions and ideas in the comments. Subscribe, tap the notification bell, and join our community as we patiently build the frameworks and plans that will welcome the galaxy's next traveler. Follow along for ongoing updates from JWST, Hubble, and Mars-based observers as new data arrive, and help us crowdsource interpretations in real time. Your engagement helps us keep the conversation alive, turn data into understanding, and ensure that when the next interstellar object appears, we're not just watching, we're ready to learn, explore, and respond together.